Above and below our solar system there is something vast, something structured, something that has been there since before the sun ignited, and we have only just begun to understand what it is. Most people, when they picture the solar system, picture a flat disk, planets arranged in a neat orbital plane circling the sun in an orderly procession. Mercury closest, Neptune farthest, everything tidy, everything contained. That picture is wrong, not partially wrong, not slightly oversimplified. Wrong in a way that, once corrected, makes the solar system look profoundly, terrifyingly different. Different in its size, different in its structure, different in its relationship to the galaxy around it and the forces that shaped every planet, every moon, every comet that has ever fallen toward the sun. Above our solar system, in the direction astronomers call galactic north, stretches a region of space so extreme, so ancient and so strange that it challenges the definition of what the solar system even is. And below, in the direction of galactic south, lies something that may have been sculpting life's possibilities on Earth for billions of years without anyone noticing. The solar system doesn't end where we thought it did, and what surrounds it, above, below, in every direction beyond the familiar plane, is the most remarkable, most underexplored volume of space in our cosmic neighborhood. If space fascinates you, a like and subscribe means everything to us. Let's begin. For most of human history, the solar system was a mystery measured in naked eye observations and careful arithmetic. Ancient astronomers tracked the wanderers, the planets, against the fixed backdrop of stars and mapped their motions with impressive precision, long before anyone understood what those motions meant. The heliocentric model, formalized by Nicholas Copernicus in 1543 and refined by Johannes Kepler and Galileo Galilei in the decades that followed, established that the planets orbit the sun in ellipses, arranged in a roughly flat plane called the ecliptic. That flatness made sense. It had a physical explanation rooted in the solar system's origin. 4.5 billion years ago, a rotating cloud of gas and dust, a solar nebula, began to collapse under its own gravity. As it collapsed, conservation of angular momentum caused it to spin faster and flatten. The way a spinning pizza dough stretches outward as the chef throws it into the air. The material in the flattening disk eventually coalesced. The dense central concentration ignited as the sun and the remaining material in the disk accreted into the planets, moons, asteroids, and other bodies we recognize today. This is why the planets all orbit in roughly the same plane, all traveling in roughly the same direction. They share the rotational inheritance of the original collapsing cloud. For a long time, that was essentially the whole picture. The solar system was the sun, the planets, and the sparse cloud of debris that trailed between them. Everything orbited in the ecliptic plane. Everything was, by cosmic standards, local and compact. Then we started looking farther. The first profound expansion of the solar system's known boundaries came in 1950, when Dutch astronomer Jan Oort proposed something remarkable. He was studying the orbital patterns of long-period comets, those comets with orbital periods of hundreds or thousands of years that appear to arrive from all directions in the sky, not just from the ecliptic plane. If the solar system were purely a flat disk, comets should come preferentially from directions within that disk. But they didn't. They came from everywhere, above, below, from every angle. Oort's explanation was elegant and staggering. The solar system must be surrounded by a vast, roughly spherical cloud of icy objects, extending far beyond the known planets in all directions. Not a disk, a shell, an enormous, as diffuse reservoir of primordial ice and rock left over from the solar system's formation, occupying a sphere stretching from perhaps 2,000 astronomical units, 2,000 times the Earth-Sun distance, out to as far as 100,000 astronomical units, nearly 2 light-years. This was the Oort cloud. To understand the scale of what Oort proposed, consider this. The distance from the Sun to Neptune, the outermost recognized planet, is approximately 30 astronomical units. The inner edge of the Oort cloud, by current estimates, begins at roughly 2,000 astronomical units, more than 60 times farther than Neptune. The outer edge extends to distances comparable to a quarter of the way to the nearest star. The solar system in 3 dimensions is not a flat disk. It is an enormous sphere. with the familiar planetary plane as a thin wafer at its centre. What is above and below that wafer? What occupies the vast volume of the Oort cloud? How does it connect to the galaxy surrounding it? And what forces, from galactic distances, reach down into that cloud and hurl comets inward toward the Sun, toward us, in cycles that have been shaping the inner solar system for billions of years? These questions, once purely theoretical, have in recent decades become accessible to direct investigation, and the answers are more extraordinary than Oort, or anyone who followed him for the next 50 years, could have imagined. Let's establish the geography first. The solar system has a plane, the ecliptic, but it also has an orientation relative to the galaxy. The Milky Way itself is a flat disk of stars, and roughly 100,000 light-years across and perhaps 1,000 light-years thick, with our Sun positioned about 26,000 light-years from the galactic centre. The solar system's ecliptic plane is tilted at roughly 60 degrees relative to the galactic plane, so above and below the solar system's own plane is different from above and below the galaxy's plane. Both orientations matter. Both directions contain remarkable, distinct, profoundly important things. In the direction perpendicular to the ecliptic, straight up and down from the planetary disk, lies the full, three-dimensional expanse of the Oort cloud. Icy, ancient, tenuous. Objects here move in orbits so enormous that a single orbital period takes millions of years. They're effectively stationary on any human timescale, drifting in slow gravitational equilibrium. In the direction perpendicular to the galactic plane, galactic north and south, lies the disk halo interface, the region where the orderly star-forming disk of the Milky Way gives way to the ancient metal-poor diffuse stellar halo that envelops the entire galaxy. A region of ancient globular clusters, of high-velocity stars, of dark matter concentrations that warp the galaxy's structure, of a magnetic field that threads through space in geometries we are still mapping, and threading through both regions, through the Oort cloud and the galactic halo interface both, is something else, something invisible, something that passes through the solar system on a cycle of roughly 26 to 30 million years, each passage sending disturbances rippling through the Oort cloud and potentially driving comet showers into the inner solar system. The identity of this periodic disturber has been one of the most contentious and fascinating debates in planetary science for 4 decades. A companion star, a hidden planet, the gravitational tide of the galaxy itself. Each theory has evidence for it, each has gaps, and the resolution, partial, incomplete, but genuinely illuminating, is one of the most extraordinary stories in the recent history of solar system science. But before we get there, we need to understand what actually lives in the three-dimensional solar system above and below the ecliptic plane. Because the Oort cloud is not empty, and it is not passive. The Oort cloud contains, by current estimates, somewhere between 1 trillion and several trillion individual objects, comets, icy planetesimals, frozen remnants of the solar system's early formation. The total mass is uncertain but relatively modest, perhaps a few times the mass of Earth, spread across a volume of space that is almost incomprehensibly vast. The average distance between objects in the Oort cloud is roughly 20 times the distance between the Earth and the Moon. For a region containing 1 trillion objects, it is extraordinarily sparse. No spacecraft has ever reached the Oort cloud. Voyager 1, humanity's most distant artificial object, launched in 1977 and travelling at roughly 17 kilometers per second, will reach the estimated inner edge of the Oort cloud in approximately 300 years. It will take 30,000 years to pass through the cloud entirely and emerge the other side. At human technological timescales, the Oort cloud is effectively unreachable, and yet we know it is there. We infer it from the comets it sends us. What disturbs those comets? What reaches into the outer solar system, perturbs the delicate gravitational equilibrium of Oort cloud objects, and sets them on trajectories that eventually bring them screaming past the Sun? The answer involves forces operating on galactic scales, forces that connect our local solar system to the vast, slowly rotating structure of the Milky Way itself. But that's not the full story, because in the past decade, a new generation of instruments, including the Gaia Space Observatory, which has mapped the positions and motions of nearly 2 billion stars with unprecedented precision, the WISE and NEO-WISE infrared surveys, and the expanding reach of the Vera C. Rubin Observatory's legacy survey of space and time has begun revealing the three-dimensional structure of our cosmic neighbourhood with a clarity that previous generations could only dream of. And what that clarity reveals about the space above and below our solar system is something that even the most informed researchers find genuinely startling. What we thought we knew was incomplete in ways that are not trivial. What we are discovering is not just filling gaps, it is redrawing the map. To understand what exists above and below our solar system, you have to think like a gravitational physicist. You have to abandon the intuitive human sense of space as emptiness and replace it with a more accurate picture. Space as a medium permeated by gravitational fields, magnetic fields, radiation pressures, and the slow, majestic tidal forces of structures so large that their influence operates over millions of years. Gravity doesn't stop working at the edge of the solar system. The Sun's gravitational influence extends to roughly 1 to 2 light-years, the outer boundary of the Oort cloud, where the Sun's pull becomes comparable in strength to the combined gravitational effect of nearby stars and the galaxy itself. But other gravitational influences reach inward from even greater distances, and the most important of these, the one that has most profoundly shaped the Oort cloud and through it, the history of cometary bombardment in the inner solar system, is the gravitational tide of the Milky Way galaxy. What is a galactic tide? The concept is analogous to ocean tides, but operating on a scale that defies easy visualization. Earth's oceans experience tides because the Moon's gravitational pull is slightly stronger on the near side of Earth than on the far side. This differential pull, stronger here, weaker there, produces a stretching force that raises bulges on opposite sides of the planet. Ocean tides are the expression of this differential gravity. Now scale that concept up by a factor of roughly 10 billion. The Milky Way galaxy is not a uniform sphere of mass. It is a flattened disk, denser at the centre and less dense toward the edges, denser in the galactic plane and less dense above and below it. Our solar system, embedded in this disk, experiences a gravitational pull that is stronger toward the galactic plane than away from it. This differential, this tidal force, acts on the Oort cloud continuously, and deforming it in subtle but consequential ways. In the vertical direction, perpendicular to the galactic plane, which corresponds roughly to above and below the ecliptic of our solar system, the galactic tide acts like an enormous slow hand squeezing the Oort cloud. Objects in the outer Oort cloud with orbits tilted out of the galactic plane experience a gentle but persistent gravitational nudge back toward the plane. Over millions of years, this nudge can change the orientation of an object's orbit enough to bring its closest approach to the Sun, its perihelion, significantly inward. An Oort cloud object that begins with a perihelion of, say, 5,000 astronomical units can, under sustained galactic tidal influence, end up with a perihelion of 5 astronomical units, inside the orbit of Jupiter, where the Sun's heat vaporizes its ice, and we see it as a long-period comet blazing across the sky. The galactic tide is, in a very real sense, the mechanism by which the galaxy reaches into our solar system and sends us comets. Physicist Heikki Salo and researcher Piet Hout, along with dynamicist Mark Heisler at Princeton, formalized this understanding in landmark papers published in the 1980s and early 1990s. Their models demonstrated that the galactic tide could explain a substantial fraction of the observed flux of long-period comets into the inner solar system. The galaxy, they showed, is not a passive backdrop to solar system history, it is an active participant. Now here's where it gets truly strange. The galactic tide is not constant. As the Sun orbits the galactic centre, a journey that takes approximately 225 to 250 million years to complete, a period sometimes called the galactic year, it doesn't travel in a perfectly flat circle within the galactic plane. Instead, it oscillates up and down, bobbing above and below the galactic plane like a cork on a gently rippling sea. The Sun is currently below the galactic midplane by about 50 to 100 light-years, travelling upward toward the midplane and expected to cross it in roughly 3 million years. Each time the Sun crosses the galactic plane, it passes through a region of higher stellar density. More stars, more molecular clouds, more concentrated mass. The galactic tide strengthens, the perturbations on the Oort cloud intensify, and the rate at which Oort cloud objects are sent sunward and potentially earthward, increases. The period of this galactic oscillation is roughly 30 to 35 million years, depending on the assumed density structure of the galactic disk. Does that number sound familiar? It should. Because in 1984, paleontologists David Rout and Jack Sepkoski published a now famous analysis of marine fossil records in the Proceedings of the National Academy of Sciences. Examining the timing of mass extinction events over the past 250 million years, they found a periodicity in extinction rates, a pulse of elevated extinction appearing roughly every 26 million years, not every single time, not with clockwork precision, but statistically, persistently, undeniably, 26 million years. The match to the galactic oscillation period, 30 to 35 million years in some models, closer to 26 in others depending on parameter choices, is striking, provocative, contested. The hypothesis that followed is one of the most audacious in all of Earth science, that the periodic crossing of the galactic plane, by perturbing the Oort cloud and driving elevated comet flux toward Earth, has been triggering mass extinctions on a regular cycle for hundreds of millions of years. That the great dying events in Earth's history, the end Permian, the end Cretaceous, the end Triassic, are not random catastrophes, but the periodic expressions of our solar system's galactic orbit. That what happens above and below the solar system doesn't just shape the cosmos, it shapes life. This remains genuinely debated. The statistical signal in the extinction record has been questioned by researchers who argue the periodicity is not robust when the data set is examined with different statistical methods. The comet flux increase predicted by the galactic tide, while real, may not be large enough to reliably produce extinction-level impacts on a regular schedule. Alternative explanations for each of the major extinction events, volcanism, climate change, sea level variation, have substantial evidential support. But the correlation exists, the physics is real, the mechanism is plausible, and the implication that the history of life on Earth is written partly by the structure of the galaxy itself is profound in a way that doesn't diminish with scientific scrutiny. What else reaches down from above? The galactic magnetic field. Magnetic fields are not merely local phenomena. They thread through space at every scale, from the terrestrial field that deflects charged particles away from Earth's surface, to the heliospheric field generated by the solar wind and extending to the outer edge of the solar system, to the galactic magnetic field that permeates the entire disk of the Milky Way. This galactic field has a characteristic strength of roughly 1 to 2 microgauss, fantastically weak by terrestrial standards, but operating over volumes so vast that its cumulative effects are significant. Above and below the galactic plane, in the directions that correspond to the Oort cloud's vertical extent, the galactic magnetic field changes geometry. In the midplane, the field runs primarily parallel to the galactic disk. Above and below the disk, the field lines begin to flare outward, escaping the disk structure and extending into the galactic halo. The interface between the disk field geometry and the halo field geometry occurs at roughly the same altitude above the galactic plane where our solar system currently sits. This field geometry matters for the Oort cloud in a way that is only beginning to be understood. Charged particles, cosmic rays, are deflected by magnetic fields. Their trajectories spiral along field lines. The geometry of the magnetic field above and below the solar system determines, in part, from which directions cosmic rays reach us. And cosmic rays, as we'll explore in more depth, are not merely a radiation hazard. They are a source of ionization in the upper atmosphere, a driver of cloud formation, according to some contested but persistent research, a potential modulator of Earth's climate. The space above and below our solar system is not a void. It is a structured environment threaded with magnetic geometry, permeated by gravitational tides, carrying the streaming flux of energetic particles from across the galaxy. And all of this reaches down through the Oort cloud, through the heliopause, the outer boundary of the Sun's influence, and ultimately, on the longest timescales, into the inner solar system where we live. To put this in perspective, every time a long-period comet appears in our night sky, Comet Hale-Bopp in 1997, blazing in the northern hemisphere, Comet McNaught in 2007, the brightest comet in 40 years, it is a messenger from this outer realm, An Oort cloud object disturbed by galactic forces set on a million-year journey inward, carrying water ice and organic molecules and silicate dust that are chemically indistinguishable from the material that built the planets. Looking at a comet is looking at the Oort cloud. It is looking at the space above and below our solar system, made briefly visible. But here is the finding that changes everything. The one that the galactic tide models, impressive as they are, don't fully account for. The Oort cloud is not the only structure above and below the solar system, and galactic tides are not the only forces acting on it. Beginning in the 1970s, researchers studying the detailed orbital distribution of a long-period comets noticed something that the galactic tide alone couldn't explain. Certain comets arrived with orbital parameters that suggested they had been perturbed much more recently than a steady tidal effect would produce. Their energy states were close to parabolic, barely bound to the Sun, suggesting they had entered the inner solar system for essentially the first time from the deep Oort cloud. But the direction of their arrival wasn't uniformly distributed across the sky as a steady tidal perturbation would produce. There were clustering patterns, subtle but statistically detectable concentrations from specific sky directions. Something discrete, not diffuse, was disturbing the Oort cloud. The candidates were several. First proposed, a yet undiscovered companion star to the Sun. A distant dim stellar companion, a red dwarf, a brown dwarf, or a white dwarf, orbiting the Sun at Oort cloud distances, sweeping through the cloud at regular intervals and gravitationally scattering objects into the inner solar system. This hypothetical companion was named Nemesis, after the Greek goddess of retribution. Physicist Richard Muller at the University of California, Berkeley, was among its principal advocates in the 1980s. The Nemesis hypothesis offered an elegant, physically simple explanation for both the comet clustering and the apparent periodicity of mass extinctions. Nemesis was searched for extensively. Infrared sky surveys were designed with the specific sensitivity required to detect a dim stellar companion at distances of 1 to 2 light-years, the 2-micron all-sky survey. The Wide Field Infrared Survey Explorer, WISE, launched in 2009 with the sensitivity to detect even a cold brown dwarf at Nemesis distances. In none of these surveys found a stellar companion. The searches were not definitive. A sufficiently dim, sufficiently cool object at the outer limits of the Oort cloud remains detectable only with difficulty, but the WISE survey in particular set limits that make a luminous stellar companion highly unlikely. A more exotic proposal, a Planet 9. In 2016, planetary scientists Konstantin Batygin and Mike Brown at the California Institute of Technology published a landmark paper in the Astronomical Journal. They had been analysing the orbital clustering of a class of distant trans-Neptunian objects, small bodies orbiting beyond Neptune in the scattered disk and extended scattered disk, and found that their orbital orientations were not random. They were clustered, aligned in a way that statistically was too coherent to be coincidence, where the alignment suggested gravitational shepherding by a massive distant unseen body, a planet with perhaps 5 to 10 times Earth's mass, orbiting the Sun at an average distance of perhaps 400 to 800 astronomical units, well inside the inner Oort cloud. Planet 9, or Planet X, as it has been called in various iterations of this hypothesis throughout astronomical history. If Planet 9 exists, it would not be the outermost planet in a flat disk sense. It would be a significant mass perched at the inner edge of the Oort cloud, with an orbit so eccentric, so elongated, that it ranges from relatively close approaches to the Sun out to the vast distances above or below the ecliptic plane. Its gravitational influence at Oort cloud distances would be significant. Not enough alone to explain all the periodic comet injection that has shaped Earth's history, but enough to produce the orbital clustering observed in distant trans-Neptunian objects. And if it exists, it changes the picture of what lives above and below our solar system in a fundamental way. Because Planet 9 would not be in the ecliptic plane. Its proposed orbit is inclined at roughly 15 to 25 degrees to the ecliptic and is highly eccentric. At its farthest point from the Sun, its aphelion, it would be positioned hundreds of astronomical units above or below the ecliptic plane. A genuine resident of the three-dimensional outer solar system, a massive frozen world orbiting in the dark, far above the familiar plane of the planets. The search for Planet 9 is ongoing. As of the mid-2020s, the Vera C. Rubin Observatory, an extraordinary wide-field telescope in Chile that began science operations and will eventually survey the entire accessible southern sky to unprecedented depth, is expected to either detect Planet 9 if it exists, or place sufficiently tight constraints on its non-detection to rule it out. The result will be definitive. The implications of this discovery are almost too vast to comprehend, because whether Planet 9 exists or doesn't exist, the search for it has been the most intensive investigation of the outer solar system in history. And in that investigation, the sky above and below the ecliptic, the three-dimensional solar system, has been mapped with greater precision than ever before. Thousands of distant trans-Neptunian objects have been discovered. Their orbital architecture has been measured, and what that architecture reveals about the history of the outer solar system is a story that has been hiding in plain sight for decades, waiting for the instruments powerful enough to read it. Before we go to the Oort cloud, before we reach the edges of the solar system's gravitational territory, there is something closer, something that sits above and below the planetary disk at distances of only a few hundred astronomical units, something that has been directly sampled by human-made spacecraft, and whose properties are so unexpected that engineers and physicists spent years arguing about what the data meant. It is called the heliopause, and passing through it, in the final years of their operational lives, two of the most remarkable objects humanity has ever built discovered something about the space above and below the solar system that nobody had predicted. The Sun does not simply sit in interstellar space, it generates a vast bubble of influence. From the solar corona, a continuous outflow of charged particles, electrons, protons, helium nuclei, streams outward in all directions at speeds of 400 to 800 kilometers per second. This is the solar wind. It fills the inner solar system, shaping cometary tails, driving auroral displays on magnetized planets, and creating a vast magnetized bubble that extends outward into the space between stars. This bubble is called the heliosphere. At its outer boundary, the heliopause, the outward pressure of the solar wind exactly balances the inward pressure of the interstellar medium, the sparse gas and plasma that fills the space between stars. The heliopause is the true outer boundary of the Sun's direct influence. Beyond it, the Sun's particles no longer flow outward. You are in interstellar space. Voyager 1 crossed the heliopause in August 2012 at a distance of approximately 121 astronomical units from the Sun. Voyager 2 launched on the same day as Voyager 1 in 1977, but on a different trajectory, swinging through the outer solar system in a grand tour of the giant planets, crossed the heliopause in November 2018 at a distance of approximately 119 astronomical units, but in a completely different direction. And here is what they found on the other side. The interstellar medium in the vicinity of the solar system is not uniform. It is not the cold, featureless void that popular imagination pictures between the stars. It is a structured, dynamic, chemically rich environment with distinct regions, distinct temperatures, distinct magnetic field orientations. The immediate neighbourhood of our solar system is occupied by a region known as the local interstellar cloud, sometimes called the local fluff, a diffuse cloud of warm, partially ionized hydrogen and helium, roughly 30 light-years across, through which the Sun is currently travelling. Temperature within this cloud, approximately 6,000 Kelvin, comparable to the surface of the Sun. Density, roughly 1/10 of an atom per cubic centimetre. Essentially a vacuum by any terrestrial standard, but nonetheless a real, measurable, a structured medium. The local interstellar cloud is embedded within a larger structure, the local bubble. This is an enormous region, roughly 300 light-years across, of extremely hot, extremely low-density plasma. Temperature, approximately 1 million Kelvin. The local bubble was carved over the past 10 to 20 million years by a series of supernova explosions from massive stars that have since died. The blast waves from these supernovae swept the local interstellar medium outward, creating a cavity, a bubble, in which our solar system is essentially floating. Above and below the solar system, in the direction perpendicular to the galactic plane, the local bubble opens up. It is not perfectly spherical. It is elongated, extending more significantly in the direction of galactic north and south than within the galactic plane. This asymmetry means that the solar system's passage through the local bubble, and eventually in tens of millions of years out of it, will happen differently depending on direction. Above, the boundary of the local bubble is more distant. Below, interactions with adjacent bubble structures are more complex. The Voyager data revealed something even more remarkable about the heliosphere's geometry. The heliosphere is not a perfect sphere. It is not even close. The solar wind doesn't push equally hard in all directions, and the interstellar medium doesn't push back equally. The heliosphere is compressed on the side facing the sun's direction of travel through the galaxy, the bow of our cosmic ship, and extended on the trailing side. More importantly, the shape above and below the ecliptic plane differs from the shape within it. Voyager 1 exited through the top of the heliosphere, roughly perpendicular to the ecliptic, heading in the direction of the constellation Ophiuchus. Voyager 2 exited through the bottom, in the direction of the constellation Telescopium. They crossed the heliopause at similar distances, 121 versus 119 astronomical units, but the properties of the interstellar medium they encountered were measurably different. The magnetic field direction in the interstellar medium at Voyager 1's exit point differed from that at Voyager 2's exit point. The particle populations were different. The temperature profiles of the crossing itself were different. The heliosphere is not symmetric above and below the ecliptic in the way that simple models predicted. Something in the structure of the surrounding interstellar medium, the local fluff. The local bubble, the larger galactic magnetic field geometry, creates a distinct environment above versus below. This asymmetry has direct consequences for the Oort cloud. Because the heliosphere modulates the flux of interstellar particles, including galactic cosmic rays, that reaches into the solar system. In directions where the heliosphere is more compressed, cosmic ray intensities are higher. In directions where it is more extended, the shielding is more effective. The three-dimensional structure of the heliosphere, shaped by the interstellar environment above and below, creates a directionality in cosmic ray flux that influences the radiation environment throughout the solar system, including on Earth. Some might wonder whether variations in cosmic ray flux at the level produced by heliospheric asymmetry are significant enough to matter for anything. The answer, surprisingly, is yes, not in the acute radiation dose sense that concerns spacecraft designers, but in a subtler, more pervasive sense. Cosmologist Nir Shaviv at the Hebrew University of Jerusalem and geologist Jan Weiser at the University of Ottawa published research in 2003 in the journal GSA Today, proposing that the Earth's climate over geological timescales correlates significantly with cosmic ray flux. Their argument: cosmic rays ionize the lower atmosphere, producing aerosol particles that seed cloud formation. More cosmic rays, more clouds, higher albedo, cooler climate. Less cosmic rays, fewer clouds, lower albedo, warmer climate. This hypothesis, known as the cosmic ray climate link, is genuinely controversial. The direct experimental evidence for cosmic ray-driven cloud formation at the level required to drive significant climate change is debated intensely within the atmospheric science community. The cloud experiment at CERN has investigated the mechanism under controlled conditions, with results that demonstrate the phenomenon is real, but its magnitude in natural conditions remains contested. But the connection between solar system position, galactic cosmic ray flux and terrestrial climate is not fringe science. It is a legitimate, active research program connecting the physics of the interstellar medium, the space above and below our solar system, to the history of Earth's climate over hundreds of millions of years. Now we arrive at the most extraordinary structure of all, the Oort cloud, 1 trillion objects, 2 light-years of radius, ancient beyond most conceptions of ancient. These objects were assembled in the first few million years of the solar system's existence, before the giant planets had fully formed, before the late heavy bombardment, before the first single-celled organisms appeared in Earth's oceans. They have been orbiting in the dark for 4.5 billion years, essentially unchanged, essentially undisturbed, preserving the chemical composition of the protosolar nebula in a natural deep freeze. What do we actually know about what's up there? We cannot see individual Oort cloud objects. Even the most powerful telescopes cannot detect them at those distances. They're too small, too dark, too cold, too distant. Everything we know about the Oort cloud is inferred from the comets it sends us and from dynamical models of how the outer solar system evolved. but the inference is remarkably detailed. The Oort cloud appears to have two distinct structural components. The outer Oort cloud, extending from roughly 20,000 to 100,000 astronomical units, is roughly spherical, containing objects in orbits oriented randomly in all directions. These are the ones most susceptible to galactic tidal perturbations and stellar encounters. They are the reservoir from which long-period comets are drawn. The inner Oort cloud, extending from roughly 2,000 to 20,000 astronomical units, is more disk-like, retaining some memory of the flat structure of the original solar nebula from which it formed. Objects here are less susceptible to galactic perturbation, but may be influenced by a massive outer perturber such as Planet 9, if it exists. How did the Oort cloud form? It was not assembled in place. The objects now populating the outer Oort cloud were originally formed in the giant planet region, in the zone where Jupiter, Saturn, Uranus and Neptune formed, and were gravitationally ejected outward by close encounters with the giant planets during the turbulent early solar system. Computer simulations by Harold Levison at the Southwest Research Institute and his colleagues have traced this ejection process in detail. The young giant planets, migrating through the protoplanetary disk, scattered planetesimals outward. Most were ejected entirely from the solar system, flung into interstellar space. But a fraction, a few percent, were captured in the Oort cloud, their orbits modified by galactic tides and stellar encounters that circularized and expanded them to the vast dimensions we observe today. The solar system above and below the ecliptic is, in a profound sense, the graveyard of objects that failed to become planets, the material that didn't make it into the Earth, or Venus, or Jupiter, the leftovers of creation stored in a vast spherical archive above and below everything we know. And here is the connection that ties all of these threads together. The comets that the galactic tide delivers into the inner solar system are not merely spectacular sky shows or impact threats. They are time capsules. The chemistry of comets, measured in exquisite detail by the European Space Agency's Rosetta mission, which orbited comet 67P/Churyumov-Gerasimenko from 2014 to 2016, and the instrument aboard the Philae lander that made the first ever touchdown on a cometary surface, reveals organic molecules of extraordinary complexity. Glycine, the simplest amino acid. Phosphorus, a key constituent of DNA and cell membranes. Water ice with a deuterium to hydrogen ratio that partially matches Earth's oceans. Complex carbon compounds including polycyclic aromatic hydrocarbons. The origin of life on Earth is one of science's deepest unsolved questions. One persistent hypothesis, panspermia in its soft form, or more precisely cometary delivery of organics, proposes that some fraction of the molecular building blocks of life arrived on early Earth aboard comets and asteroids during the late heavy bombardment, 3.8 to 4.1 billion years ago. This bombardment, which scarred the surfaces of every inner solar system body including the Moon, coincided with the period when life appears to have first emerged on Earth. The bombardment material came, at least partly, from the outer solar system, from the Oort cloud and its inner counterpart, the Kuiper belt, from the space above and below the planetary plane. The implication, speculative but scientifically grounded, is that life on Earth may have been seeded, at least in molecular terms, by material delivered from above and below the solar system. Material that had travelled from the outer Oort cloud, perturbed by galactic tides operating on timescales of millions of years, falling inward over geological epochs to deliver its chemical payload to the young, volcanic, ocean-forming Earth. You, reading this, watching this. Yeah, every cell in your body. Are you made in part of Oort cloud material? Of interstellar chemistry that fell in from the dark, from above and below, from 2 light years out 4 billion years ago? The evidence doesn't confirm it, but it doesn't rule it out. And that possibility, that we are, in some molecular sense, children of the outer solar system as much as children of the Sun, is perhaps the most profound implication of everything the space above and below our planetary disk contains. Let's pause for a moment and consider what we've established. Above and below our solar system, in the full 3-dimensional space that surrounds the thin disk of the planets, there is a trillion-object reservoir of ancient ice and rock. There is a structured interstellar medium, shaped by ancient supernova explosions, through which the solar system is actively travelling. There is a galactic magnetic field in geometric transition from disk to halo. There is a gravitational tide from the galaxy itself, capable of reaching down into the Oort cloud and sending objects toward the Sun on million-year journeys. There may be a massive unseen planet on an eccentric orbit above the ecliptic, and the history of life on Earth may be entangled with all of it. But this raises an even bigger question. If the space above and below our solar system is this consequential, this active, this structured, this influential on everything from comet trajectories to mass extinctions to the origin of life, why is it so poorly observed? Why do we know so little about a volume of space that contains our nearest cosmic context? The answer is partly technological. The Oort cloud is simply too distant and too diffuse for current instruments to directly image. The interstellar medium beyond the heliopause is accessible only to spacecraft that have travelled for decades to reach it. The galactic magnetic field above and below the disk is detectable through its effects on polarized starlight and radio emission. But mapping it in 3 dimensions requires decades of painstaking multi-wavelength observation. But the answer is also partly conceptual. For most of the history of astronomy, the relevant unit was the 2-dimensional sky, the celestial sphere as viewed from Earth. Stars, planets, nebulae, all projected onto the same great dome. The 3rd dimension, depth, distance, was difficult to measure and for practical observational purposes often irrelevant. The solar system was mapped in the ecliptic plane because that's where the planets are. The galactic structure was mapped in the galactic plane because that's where the stars are concentrated. Above and below, in both senses, was the hard direction, the sparse direction, the direction with the fewest objects to observe and the fewest guides to depth. That is changing. The Gaia Space Observatory, launched by the European Space Agency in December 2013, and currently in its extended mission phase, has produced the most comprehensive 3-dimensional map of our galactic neighbourhood in the history of astronomy. By measuring the parallax, the tiny apparent shift in stellar position as Earth orbits the Sun, of nearly 2 billion stars, Gaia has produced a genuine 3-dimensional picture of the stellar environment within roughly 10,000 light-years of the Sun, including the stars above and below the galactic plane, including the density structure of the stellar disk in the vertical direction, including the precise positions and velocities of stars that have, over their lifetimes, made close approaches to our solar system and perturbed the Oort cloud. The Gaia data has already yielded a discovery that has significant implications for solar system history. Analysing the stellar trajectories reconstructed from Gaia's proper motion data, astronomer Corinne Baylor-Jones at the Max Planck Institute for Astronomy and colleagues have identified the closest stellar approach to our solar system in the past 5 million years. A star called Schultz's star, a binary system consisting of a red dwarf and a brown dwarf companion, passed within roughly 0.82 light-years of the Sun approximately 70,000 years ago. 0.82 light-years. That is within the outer Oort cloud. The passage of Schultz's star through the outer edge of the Oort cloud would have gravitationally perturbed thousands of objects in the cloud, sending some inward toward the Sun on trajectories that will arrive in the inner solar system thousands to hundreds of thousands of years in the future. We may be living in, or approaching, a period of slightly elevated comet flux driven by an encounter that happened when anatomically modern humans were in the early stages of leaving Africa. Gaia has identified several other close stellar approaches in the past and future, stars that will, within the next few million years, pass within 1 to 2 light-years of the Sun and disturb the Oort cloud in ways that dynamical models can now predict. The future of the outer solar system, the direction and intensity of Oort cloud perturbation, is calculable in principle from the current positions and velocities of nearby stars. Gaia has given us, for the first time, a meaningful predictive capacity for the long-term evolution of our cosmic neighbourhood. What about the interstellar medium immediately above and below the solar system? The solar system is currently moving through the local interstellar cloud, as we discussed earlier. This cloud is warm, partially ionized, and moving through our neighbourhood at roughly 26 kilometers per second. The Sun entered this cloud within the last 10,000 to 100,000 years. The timeline is uncertain, and is expected to exit it in perhaps 10,000 to 20,000 years. What happens when the solar system exits the local interstellar cloud into different interstellar medium conditions? The answer depends on what lies on the other side. Mapping the boundaries and properties of the local interstellar medium is a key objective of heliospheric research programs. Data from IBEX, the Interstellar Boundary Explorer, a NASA spacecraft launched in 2008 that maps the heliosphere from the inside by detecting energetic neutral atoms streaming in from the boundaries, has produced detailed maps of the heliosphere's shape and the conditions of the interstellar medium impacting it. These maps reveal a structured, non-uniform medium above and below the solar system, different regions with different densities, temperatures, and magnetic field orientations. The heliosphere's response to these varying conditions means that Earth's cosmic radiation environment has varied and will vary as the solar system moves through its local interstellar neighbourhood. The IMAP mission, Interstellar Mapping and Acceleration Probe, scheduled by NASA for launch in 2025, will take this investigation a step further, measuring the properties of the interstellar medium and the heliospheric boundary with sensitivity and angular resolution far exceeding IBEX. The picture of what surrounds us above and below at the immediate interstellar scale will become dramatically clearer within this decade. But the most dramatic expansion of our knowledge of the outer solar system above and below the ecliptic will come from the Vera C. Rubin Observatory. Over its 10-year legacy survey of space and time, Rubin will image the entire accessible sky, from the ecliptic plane up to galactic north and down to galactic south, repeatedly, deeply, in multiple wavelength bands. Every object in the solar system brighter than a certain magnitude limit will be detected. The trans-Neptunian object population will expand from the few thousand currently known to potentially hundreds of thousands. The inner Oort cloud population, currently completely uncatalogued because no instrument has been sensitive enough to detect objects at those distances, may begin to reveal itself for the first time. If Planet 9 exists, Rubin will almost certainly find it. If Planet 9 doesn't exist, Rubin will tell us what does exist in its orbital neighbourhood, and that knowledge will be almost as valuable because it will constrain the dynamical models that describe how the outer solar system has evolved and how it has shaped the history of the inner solar system. Beyond the solar system, at galactic scales, the space directly above and below us connects to some of the most remarkable structures in the Milky Way. In the direction of galactic north, approximately 90 degrees above the galactic plane, the stellar halo extends, a vast, roughly spherical distribution of stars, globular clusters, and dark matter extending to distances of tens of thousands of light years. These halo stars are the most ancient in the galaxy, as many with ages exceeding 12 billion years formed when the Milky Way itself was young, less than 2 billion years after the Big Bang. Their chemical compositions are strikingly different from disk stars. Metal poor, enriched only with the hydrogen, helium and trace lithium produced in the Big Bang itself, plus the contributions of only the earliest generations of massive short-lived stars. The stellar halo is the galaxy's archaeological record. Reading its structure, the streams and shells of stars that trace ancient merger events, the globular clusters distributed above and below the disk in patterns that encode the Milky Way's formation history, is one of the primary sciences of the Gaia era. Directly above and below our solar system, at distances of only 50 to 150 light years, the transition between the thin disk and the thick disk of the Milky Way is occurring. The thin disk, where we live, is the young, star-forming, metal-rich layer of the galaxy, only about 1,000 light-years thick. The thick disk, extending to roughly 3,000 light-years above and below the mid-plane, is older, chemically distinct, kinematically hotter, its stars moving with greater random velocities relative to the galactic centre. The thick disk formed early in the galaxy's history, perhaps during a violent merger event several billion years ago. The transition from thin to thick disk is happening right now, in the vertical direction from our position. Above and below us, the stellar populations are changing. The age distribution of stars shifts, the chemistry shifts, the dynamics shift. If you could travel straight up from the solar system for a few hundred light years, you would move from our young, active galactic neighbourhood into a region of older, more chemically primitive stars that formed when the Milky Way was in a completely different phase of its evolution. And then, at roughly 500 to 1,000 light-years above the galactic plane, you would enter the zone of galactic fountain material. The galactic fountain is one of the most visually spectacular and least publicly known phenomena in the Milky Way. In the galactic disk, Massive stars live short, brilliant lives and die in supernova explosions. These explosions are energetic enough to drive hot gas, plasma at temperatures of millions of degrees, upward out of the galactic disk, into the region above and below the star-forming layer. This hot gas expands upward, cools as it rises, and eventually falls back down toward the disk, a vast, slow circulation of material that cycles between the disk and the galactic halo on timescales of tens of millions of years. Above our solar system, in the direction of galactic north, this fountain material is present. Radio and X-ray observations have mapped the distribution of this hot, outflowing and inflowing gas in the galactic vicinity. The local bubble, which we discussed earlier, is partly a product of these supernova-driven outflows. The fossil remnants of ancient supernova blast waves, the shells of ionized gas expanding through the interstellar medium above and below the disk, structure the environment through which the solar system travels. We are not passive travelers through this environment. The properties of the local bubble affect the heliosphere. The heliosphere affects the cosmic ray environment of the inner solar system. The cosmic ray environment affects Earth's atmosphere. Earth's atmosphere affects climate. Climate affects life. The vertical structure of the Milky Way, what exists above and below the solar system's galactic neighborhood, is not irrelevant to terrestrial affairs. It is connected through chains of physical causation that span scales from light years to centimeters, from galactic to molecular, from billions of years to human lifetimes. Remarkable, ancient, profound beyond easy comprehension. We began with a flat picture, a tidy disk of planets orbiting a star, and ended somewhere dramatically different. Above the solar system, 1 trillion ancient frozen objects tracing slow gravitational arcs in the dark, stirred periodically by the tidal force of an entire galaxy. An interstellar medium shaped by long-dead stars, threaded with magnetic fields in geometric transition from disk to halo. Ancient stellar populations, galactic fountain material, the archaeological record of the Milky Way's violent formation history, written in stars above our heads. Below the solar system, the same reflected. The same ancient cloud, the same galactic tidal reach, the same interstellar medium, structured differently, responding differently to the geometry of the local bubble. A heliosphere that the Voyager spacecraft found, in crossing it from both sides, to be unexpectedly asymmetric, shaped by environmental differences above and below that our models are still working to fully explain. And threading through it all, a galactic oscillation that carries the solar system above and below the galactic plane on a 30 million year cycle, a cycle that some researchers see written in the extinction record of Earth's own life. This is what exists above and below our solar system. Not emptiness, not passive void. A structured, dynamic, magnetically threaded, gravitationally active, chemically rich environment that has been shaping our planetary history since the first ice condensed in the outer solar nebula 4.5 billion years ago. One thread remains unresolved. One question that the coming decade of observation, Rubin, IMAP, Gaia's continued data releases, the next generation of the outer solar system probes will begin to answer but cannot yet close. What is the three-dimensional structure of the inner Oort cloud? We have never seen it directly. We infer its existence from cometary orbits and dynamical models. We have not yet catalogued a single confirmed inner Oort cloud object. The orbital architecture of this region, which lies between the outer planets and the dynamically active outer Oort cloud, may contain the answer to whether Planet 9 exists, the answer to why the mass extinction record shows the periodicity it shows, and perhaps the answer to how the Oort cloud acquired its present structure during the chaotic early solar system. Above and below us, at distances our spacecraft will not reach for centuries, that archive waits, unchanging, patient, carrying the chemical record of the solar system's birth in ice that has not melted since the sun first ignited. As we continue to look up and look down, the universe will continue to reveal that the solar system is not a closed system. It is embedded, connected, threaded through with forces from beyond, shaped by a galaxy it orbits and a local neighborhood it travels through on timescales that make human history vanish into a single heartbeat. We are not separate from the cosmos above and below us. We are made of it.